Welcome back to G Fun Facts Online, where we dive deep into the most mind-bending corners of science and mathematics. Today, we're tackling a problem that sounds simple enough but has stumped geniuses for centuries, and its solution is unlocking secrets to how we communicate in our digital world. Ever tried to cram as many oranges as possible into a box? That, in essence, is sphere packing. But what happens when you try to pack spheres not in 3 dimensions, but in 4, 8, 24, or even hundreds of dimensions? Stick around, because things are about to get weird, wonderful, and surprisingly relevant. So, packing spheres. In our everyday 3-dimensional world, we kind of know how to do it best. Think of how grocers stack oranges or cannonballs are piled, that classic pyramid shape. That's called the face-centered cubic lattice, and it fills about 74% of the space. It took until 2017 to formally prove this was the best way, a problem first posed by Johannes Kepler way back in 1611. That's a long time for oranges. But here's where it gets truly fascinating. For centuries, these 1D, 2D, and 3D solutions were all we had. Then, in 2016, a mathematical earthquake. Ukrainian mathematician Marina Vyazovska cracked the code for 8 dimensions. Yes, 8! She proved the E8 lattice was the king of packing in 8D. And she didn't stop there. Soon after, with collaborators, she conquered 24 dimensions, showing the Leech lattice was optimal. These weren't just small steps. They were revolutionary leaps, using brand new mathematical tools. But hold on, what about dimensions 4, 5, 6, 7, or 9, or 100? For most other dimensions, the perfect packing strategy is still a giant question mark. It's like having a map with only a few cities filled in and vast unexplored territories. So, what do mathematicians do? They set up bounds, like saying, okay, we don't know the exact answer, but it's definitely more than this, and less than that. And just this year, in 2024, Dr. Matthew Jensen and his team announced the biggest improvement to the more than this part, the lower bound, for high dimensions since 1947. Almost 80 years, and how did they do it? By looking at random, messy, unstructured packings, not just the neat, orderly ones. Their work even lined up with predictions from a Nobel laureate. It seems sometimes a little bit of chaos can be surprisingly efficient. And the quest doesn't stop there. Scientists are throwing all sorts of creative tools at this problem. Some are using graph theory, think complex networks, to build super disordered packings. Others are using fancy statistics, like stochastic processes, to design special shapes that help find denser arrangements. Even algorithms originally designed for cleaning up images are now being adapted to try and cram those higher dimensional spheres just a little bit tighter. It's a real mathematical melting pot of ideas. Now you might be thinking, okay, 8-dimensional spheres are cool, but what does this have to do with my life? Get ready for the surprise twist. This abstract math has incredibly practical uses, especially in something called information theory, which is the backbone of how your phone, your Wi-Fi, and even space probes like Voyager send and receive data reliably. Imagine sending a message, a text, a photo, a voice call. As it travels, it can get hit by noise or interference, like static on a radio. This noise can corrupt your message. Error-correcting codes are like a digital bodyguard for your data. They cleverly encode your information so that even if parts get garbled, the original message can still be pieced back together. And here's the magic link. Think of each possible message as a point in a high-dimensional space, with a sphere around it. You want to pack these message spheres as tightly as possible, without them bumping into each other. If an error messes up your transmitted message, it might move a bit, but if it's still inside the correct sphere, your device can figure out what was originally sent. The denser the packing, the more messages you can send reliably and efficiently. Those super dense packings in 8 and 24 dimensions found by Vyazovska, they directly lead to super efficient error-correcting codes in those dimensions. So, better sphere packing means clearer calls, faster downloads, and more reliable data from the depths of space. Despite these incredible breakthroughs, the general problem of sphere packing in high dimensions is far from cracked. Our 3-dimensional intuition often leads us astray. In these higher dimensions, geometry gets, well, weird. The gaps between tightly packed spheres can be unexpectedly enormous. A huge open question is whether the densest packings in most high dimensions are super orderly, like those cannonball stacks, or more random and jumbled. Right now, evidence points in both directions, depending on the dimension. So the hunt is on, exploring both perfectly structured lattices and these newer, messier, random arrangements. So from stacking fruit to sending messages across the solar system, the challenge of sphere packing shows how a seemingly simple question can lead to profound mathematical discoveries and powerful real-world technologies. It's a beautiful dance between pure curiosity and practical innovation. Who knew packing spheres could be so epic? That's all for this episode of G-Fun Facts Online. Keep asking questions, stay curious, and join us next time for more fascinating facts. Thanks for listening.